Learn like a pro.
Hey there, and welcome. Today, we're going to dive into the invisible world of acids and alkalis. You know, that tang you get from a lemon, or how soap feels so slippery? Well, those properties are everywhere, and we're about to find out how chemists make them visible. Okay, let's get right into it. So this is the big question for today. We know these things feel different, taste different, but how do we actually put a number on it? How do you measure something like sourness or slipperiness in a scientific way? Well, that's exactly what we're going to break down in this explainer.
And the answer is actually a really elegant and powerful tool that scientists use called the pH scale. You can think of it as our official measuring stick for anything and everything acidic or alkaline.
Okay, if you're studying chemistry, this is definitely a definition you'll want to remember. The pH scale, simply put, is how we measure and compare how acidic or alkaline a solution is. It's the standard language we use to talk about this stuff.
So what is the scale actually measuring? Well, it all comes down to a kind of chemical balancing act that's happening inside a solution. It's looking at the amount of two little particles, hydrogen ions, which we write as H+, and hydroxide ions, or OH-. Seriously, the whole thing is about the balance between these two.
This table right here, this tells the whole story. Let's start at the top. When you have a ton of hydrogen ions and barely any hydroxide ions, you get a really low pH number. We're talking 0 or 1. That's a strong acid. Now, as you go down the table, you can see that balance shifting. The hydrogen ions decrease, and the pH value climbs up. Right in the sweet spot, at pH 7, the number of H+ and OH- ions is perfectly equal. That's neutral. Then, as we keep going, the hydroxide ions take over, pushing the pH higher and higher into alkaline territory, all the way up to 14 for a strong alkali. So the main takeaway here is really simple. Low pH means very acidic. High pH means very alkaline.
Counting ions is great and all, but you can't exactly see them, right? So how do we see pH? This is where chemistry gets really cool and colorful. We use these special things called chemical indicators.
So what's an indicator? Think of it like a chemical chameleon, or maybe a secret agent. You add just a little bit to a solution and bam, it changes color based on the pH. It gives you this huge, obvious clue about whether you're looking at an acid or an alkali. It literally makes the invisible visible.
Now, there are a bunch of different indicators out there, but the real star of the show is the universal indicator. And why is it the star? Because it's not just one chemical, it's a carefully mixed cocktail of different indicators, and that means it can show a whole rainbow of colors across the entire pH scale. A good little trick to remember the colors? Just think of a rainbow. Roy G. Biv.
Let's follow that rainbow, starting with R for red. If you put universal indicator into a really strong acid, something with a pH between 0 and 2, it's going to turn a bold, bright red. Think danger, think stop sign, think strong acid.
As that acid gets a bit weaker, we just move along the rainbow to O and Y. That's orange and yellow. So for a pH in the 3 to 6 range, you'll see these warmer colors. If it's yellow, you still have an acid, just not nearly as powerful as the one that turned red.
And right in the middle, at a perfect pH of 7, we land on G for green. This is our neutral zone. Think pure water. It gives you this calm, pale green color. So in this case, green means you're perfectly balanced.
The moment we cross over pH 7, we're in alkaline territory, and we hit the B for blue. Weak alkalis, so things in the pH 8 to 11 range, will start to shift the indicator into these cooler, greeny-blue shades. And finally, for the really strong alkalis, we get to the end of our rainbow with V for violet. Any solution with a pH from 12 to 14 will give you this deep, rich violet or purple color. And there you have it, our chemical rainbow, from a fiery red for strong acids all the way to a cool violet for strong alkalis.
Universal indicator is awesome for getting a good idea of the pH. But you know, sometimes in a lab you don't need the whole rainbow. You just need a simple yes or no. Is it an acid or an alkali? And for that, chemists often use simpler, more specialized indicators like litmus and phenolphthalein.
Okay, let's break these two down. Litmus is a classic one you probably think of. It's super straightforward. It's red in acid and it's blue in alkali. That's it. Phenolphthalein, on the other hand, is a little trickier. It's completely colorless in anything acidic and anything neutral. It only shows its true colors, this amazing bright pink, when it's in an alkaline solution. So you can think of it like this. Litmus tells you one of two things. acid or alkali. But phenolphthalein is more like a specific alarm. It's silent until it detects an alkali, and then it goes off.
Now, as cool as color-changing chemicals are, they really only give you a range or an estimate. If a scientist needs to know the exact pH value, like, say, 4.75, they're not going to rely on a color. They'll grab a digital pH meter. This is a device that just gives you a precise number on a screen, and it takes all the guesswork out of the equation. It's really about precision versus a pretty good estimate.
All right, you've seen the scale, you've seen the colors. I think it's time to put that knowledge to the test. Let's do a quick pop quiz. You ready?
Okay, first question. Imagine you have a mystery liquid. You add a few drops of phenolphthalein, and poof, it instantly turns bright pink. So, what does that tell you? Is it acidic or is it alkaline? Have a think.
If you said alkaline, you are absolutely right. Remember, phenolphtalene's whole party trick is turning pink, but only when it's in an alkaline environment. Nice work.
Okay, question number 2. This time, you're using the universal indicator. You test a substance, and it turns orange. Based on that color, what is the approximate pH range of that solution? The answer is a pH of around 3 to 4. If you think back to our rainbow, red was for the strongest acids, and yellow was for the weaker ones. So orange fits right there in the middle. That tells us we're looking at a weak acid. Great job if you got that one.
All right, last question, and this one connects a couple of ideas. Let's say a cleaning solution makes a piece of litmus paper turn blue. Now, knowing that, what would you expect to happen if you then added some phenolphthalein to that same cleaning solution?
And the answer is, it would turn pink. Here's the logic. The litmus paper turning blue is our first clue. It tells us the solution is alkaline. And since we know phenolphthalein always turns pink in an alkaline solution, it has to turn pink here too. See? It's like using 2 different detectives to confirm the same story. Excellent work.
So, we've gone through the pH scale, the chemical rainbow of indicators, and how it all works. Here's a final thought to take with you. Now that you know how to spot them, where do you see acids and alkalis in action in your own life? In the kitchen? Under the sink? The world is basically a giant chemistry lab, and now you've got the tools to start exploring it.